In the last lecture, we introduced you to elements of RSA algorithm, and we pointed out that RSA algorithm uses what is known as a trapdoor function. We defined a trapdoor function to be one where the function is easy to calculate in one direction, but is a hard problem to compute its inverse. And we pointed out as an example that multiplication of two large primes is a polynomial time or an easy problem, whereas given a composite number which is known to be a product of two large prime numbers, to find its integer factors is what is known as a hard problem. At least till source algorithm of quantum computing, we have absolutely no way of factorizing a number, a composite number in a polynomial time. Now, in order to see how RSA use this fact to develop an unbreakable code, we were looking at certain elements which are required for establishment of RSA algorithm. And last time I proved what is known as a Fermat's little theorem, as is shown in the slide. We said that for a prime number p and a belonging to any set in the integer such that a is not divisible by p, we have a to the power p minus 1 is equal to 1 mod p. So this was Fermat's little theorem. A to the power p minus 1 is equal to 1 mod p. If a is not divisible by p. The next thing that we started talking about, as is shown in the slide, is Euler's totient function. As we explained last time, Euler's totient function phi of n is the number of integers which are less than the argument of the function, namely n, which have no common factors with n. This is one uses this phrase saying which are co-prime with n. And as an example, I showed you how phi of 18 happens to be equal to 6, because there are a set of 6 integers which have no common factors with the number 18, and these are one which by definition is a member of the set, 5, 7, 11, 13 and 17. Now, I have already told you these numbers themselves do not have to be prime, because two numbers may not have a common factor and they themselves need not be prime. However, if it happens that the argument of the totient function is a prime, then the value of the totient function is 1 less than the prime number itself. That is because all the numbers below it have no common factors with the argument n. Based on this, let me illustrate another theorem which is known as the Euler's theorem. The Euler's theorem states that for any integer m and an integer a such that a and m are co-prime, I must have a to the power phi m is equal to 1 mod m. The proof is very similar to the way we have proved the Fermat's little theorem, but let me do the following. Let me define the set S as all numbers which are less than phi of m, starting with 1, of course, by definition, let us call it 1 is equal to b1, which is less than b2, which is less than b3, and there are phi m of them, so less than b phi m. Now what we do is this. We say that if we multiply each element of this set by A, getting there by A, AB2, AB3, etc., etc., I would get the same set S modulo M in the way we had proved this while proving Fermat's little theorem, because we can easily show if A Bi is equal to A Bj, then I must be equal to J, Bi must be equal to Bj. Just to illustrate what I mean by that, let's take our old example of the number 18. We had said that phi of 18 consists of digits which are numbers which are 1 by definition, 5, 7, 11, 13 and 17. So phi of 18 is equal to 6. Now I am multiplying with A. Let me take A to be equal to 5. Now if I do that, I get the set S prime. Now let's see what this S prime is. So I've got 1 into 5 which is equal to 5. 5 into 5 is 25, but since I am doing my arithmetic modulo 18, this is equal to 7. 7 into 5 is 35. Modulo 18, this number is same as 17. 11 into 5 is 55, which is equivalent to 1 because 54 is divisible by 18. 13 into 5 is 65, which is equal to 11. And finally, 17 into 5 is 85, which is equal to 13. All these are mod 18. You can check immediately. I have 1, 5, 7, 11, 13 and 17, the same set. As I did in the case of Fermat's little theorem, supposing I multiply the elements of S with A, I would get this set on the right hand side, which other than for A to the power phi m factor is identical to the set S. So that tells me that A to the power phi of m must be equal to 1. Of course, mod m. So this is my Euler's theorem. The third element that I need, I will illustrate it but will not go for proving it. The proof is not difficult. I will in fact put it in the notes accompanying the lectures, but I will just illustrate this. Suppose I have a set of integers which are m1, m2 up to mk, and I have another set of k numbers which I will write as a1, a2 up to ak. So these are sets of integers and another set of integers ak. The condition on these ak's are that they are pairwise coprime. What it means is that for any I and j, I not equal to j of course, ai and aj do not have any common factors. So ai and aj are coprimes. That is what is meant by pairwise coprime. Now with this, if you look at the following set of equations, x is equal to ai mod mi. Now these are actually a set of k equations, because for every I have this. Now what the Chinese remainder theorem says is that this set of equations has a unique solutions, and this solution is given by x is equal to sum over I AI. I will explain the new quantities I am introducing, mi, yi, mod m. So AIs, of course, we have already said what they are. We define capital M as equal to the product of all the k mi's, and capital Mi is the product of all mi's other than the ith one. What it means is capital Mi is simply m divided by small mi. And finally, I need to define what is yi, and yi is mi inverse mod mi. Okay. Let my set mi be 7, 10 and 9. No common factors in mi's. Now look at this. I am looking at the following equation. Supposing I am looking at x equal to 5 mod 7, x equal to 3 mod 10 and x equal to 7 mod 9. These are the three equations I am looking for. Now my capital M becomes 7 into 10 into 9. Now multiply this with the calculator, 630. M1, leave out the 7, so 10 into 9 is 90. M2 is 7 into 9 is 63, and M3 is equal to 7 into 10 is 70. Now we defined y1 we said y1 is equal to m1 inverse. So m1 was 90, so 90 inverse mod 7. How do I solve it? This simply implies 90 y1 equal to 1 mod 7. It's very easy by inspection because I have given you small numbers. Otherwise, even if you have to do a computation, it's not all that difficult to find out what this is. Actually, you know that 91 y1 would have been divisible by 7. So therefore, it turns out that this y1 is actually equal to 6. And that's very easy to understand because 90 y1 we have, 84 is divisible by 7. So I am left with another 6 y1. So 6 y1 is equal to 1. I know 6 into 6 equal to 36, which leaves 1 when you divide it by 7. And likewise, my y2 will turn out to be equal to 7, and y3 turns out to be equal to 4. A look at the slide gives you the result. You just add up. Now you have y1, ai, yi, mi. Add this up. You get a number 5983, but our calculation is modulo capital M, so therefore it works out to 313. I leave it to you to check that this does indeed satisfy all the three equations that we wrote down. So now that we are in place for discussing what is RSA algorithm. So let me explain what is RSA algorithm. So I have two people as usual, Bob and Alice. Bob chooses to 2 arbitrarily large prime numbers. Now this is Bob's private job. He chooses P and Q, which are both primes, can be taken to be large, and he computes a number n is equal to PQ. Now this is what Bob is doing. He also calculates the number which is phi of n. Now remember, n is a factor of 2 primes, and we have already stated that if an argument of the totient function is a prime, then the number phi of n is nothing more other than 1 less than that number. So in other words, phi of capital N is simply P minus 1 into Q minus 1. As an example, which I will take small numbers obviously because I want you to calculate, be able to calculate using a calculator. Let P be equal to, let's say 7 into 5. So let P be equal to 7, Q be equal to 5, so that N is equal to 35. Next job of Bob is to, and let's also write down what is phi of this number, phi of 35, which is P minus 1 into Q minus 1, which is 6 into 4 equal to 24. So these are things which Bob calculates because he is the person who has chosen the 2 prime numbers. Bob chooses a number E, which is co-prime with this phi of 35, phi of n. The set N and E, they are called the public code for Bob. What it means is, anyone has an access to these 2 numbers, which are probably published in a directory under Bob's entry. So now, what Bob does is this. So let me give as an illustration what Bob has done now so far. So Bob has chosen P is equal to 7, Q is equal to 5, phi of 35 is equal to 24, and I am looking for a number which is co-prime with 24. Let me choose this number to be equal to 7. So E is equal to 7 I have taken. So this is my public code. What the public code means is this. Supposing I want to encode a number, M is message, M is to be encoded. The algorithm that I am talking to you about is the coding done by anyone who is interested in sending a message to Bob. And Bob has given his public key algorithm, public key, to be the number N and E. So what a person does, the person who intends to send a message to Bob, he uses M to be coded by a letter C, and that is simply done by M to the power E mod N. And he sends it through a public channel to Bob. Just to give you an illustration, let M be equal to 3. We had said E is equal to 7. So my C in this case will be 3 to the power 7 mod 35. You can use this number, you can calculate this number in a calculator. You will find this number is given by 2187 mod 35. and this will work out to 17. It's a very trivial division and the remainder will turn out to be 17. So therefore, instead of using 3, person who is sending a message to Bob, our name for this person now is Eve. So Eve uses this code and sends a message using this NE. Now Bob receives it. Bob's job is to decode it. But you remember, Bob has lot more information. Given capital N, Eve cannot factorize N. So in other words, Eve has no knowledge of the prime factors of N which Bob had said to be P and Q. Now of course, in this case, in the example I am giving, N is 35, Eve can. But on the other hand, if it is a very large number, typically 128-bit number, this is an impossible task because by definition of Trapdoor function, the factorization is not possible within polynomial time. So Bob now has to somehow or other decode this number which he received. So this was public. Now Bob's private code. Bob has E, he multiplies that with the D and determines D such that ED is equal to 1 but mod phi n. So in this particular case, my phi n was 24, which of course Bob knows. Now the thing is this, that this means since E was equal to 7, I am looking for 7D is equal to 1 mod 24. It just incidentally turns out, though it is not necessary, that D also happens to be equal to 7. You can check why. 7 into 7 is 49, 49 is 48 plus 1 and 24 of course is a factor of 48. So this is what Bob computes. And the message that he has got, C, was equal to 17. He now computes 17 to the power, actually he computes C to the power D, which is 17 to the power 7. And this turns out to be a fairly large number. In fact, I will write it down. It is 410338673. And he computes it modulo n. If you do this modulo n, modulo 35, this will turn out to be 3 mod 35 and 3 was the message itself. So this is equal to n. You can check it for any other pair of numbers that you feel like. Now what I will do is this. My next job is to simply find out why does this decoding work. So let us look at the slide again. So we are looking for C to the power D equal to M to the power ED, and I want it to be equal to M. So what it means is M to the power ED minus 1 is equal to 1 mod M. So let us look at the following. Now I am aware of the following result. By Euler's theorem, M to the power K phi n is equal to 1 mod M. This we have proved. In this particular case, since n is a product of P and Q, I have M to the power K into P minus 1 into Q minus 1. Now let us write it in this fashion. M to the power P minus 1 raised to the power Q minus 1. That's equal to 1. Okay, and so if M is not a multiple of Q, then this relationship is true by Fermat's little theorem. And if I wrote this M as M to the power Q minus 1 raised to the power P minus 1, then by parallel argument I can prove that this is also true by Fermat's little theorem for the other integer P as well. So only problem now is that C to the power D is equal to M to the power ED equal to M is true if M is not a multiple of P or Q. Now suppose M is indeed a multiple of P, then M mod P is 0 by definition. So if it is true for M, it is true for any other power as well, and this argument would also be valid for Q. So therefore, we have M to the power D is equal to M mod N. So now what we have done is this. We have shown that X is equal to M to the power DE equal to M mod P, and another equation is M to the power DE equal to M mod Q. These are two equations. But we have already said that such pairs of equations where M to the power DE has been replaced by X has a unique solution by Chinese remainder theorem. So therefore, the solution that Bob has worked out is unique, and hence the decoding works. So what we have done today is to establish the validity of public key algorithm. The key is calculated using a trapdoor function by Bob, which is to take two prime numbers, find their product n, and then determine a number E which acts as the code, and n and E are his public key. He has a private key which only he knows how to calculate, and that is D, and then if he receives a message he can easily decode it. As we pointed out earlier, that we may have to relook at the RSA algorithm if the trapdoor function, which was crucial to our argument, doesn't remain valid for the factorization case. That is, if I can use a quantum computer and if I can actually use source algorithm successfully, then of course one will need to have second thought about whether RSA algorithm is valid or not.